Okay, welcome everybody. Welcome to Manchester, welcome to the Open Day, and welcome to this talk on the physics programs here in Manchester. So my name's Dave Binks. I'm the admissions tutor for the undergraduate physics programs. I guess your guys in the middle of the process of making what is probably one of the most difficult and important decisions you've ever had to make, and that is what and where to study at university. Now, not only is that a difficult and important decision, it's also very much a personal decision. So for the right answer for one person is not necessarily the right answer for the next person. But what is true for everybody is that the more information that you have about your options, the more likely you are to make the right decision for you as an individual. So the purpose of days like today, purpose of talks like this, is for us to help you with that process as much as we can by giving you as much information as we can about the physics programs here in Manchester. So that's the purpose of this talk, to explain what exactly you'll be studying when you come to study physics, okay, how you'll be taught, what the environment's going to be like, and also what options you have for things like travel abroad or work experience, and finally what sort of careers you might expect to go on to once you graduate. All to help you make that big, important and personal decision about what and where to study at university. So the first question then of those questions is, what is physics about when you study at university? Now, of course, you've got some idea already because you're studying physics at school or college at the moment. You're spending maybe a third or a quarter of your time studying physics over 2 years. But when you come to university, you spend 100% of your time studying physics for 3 or 4 years. So that means you get to cover it in a lot more depth and a lot more breadth. So what is it you'll be studying? Or what is physics at university? Okay, well that's in many ways the easiest of the questions to answer today. Physics is about everything. All right, I mean literally everything, because one of the things we study in physics is cosmology, which is the study of the universe as a whole. So it's literally the study of everything. But it's not just that, of course. It's about study at all sorts of scales less than the universe. So we study the universe as a whole in cosmology. We study astrophysics, galaxies and stars and planets. We also study the things on the everyday scale of human experience, things you can hold and touch. But we also study on things on a scale much, much smaller than that. We study molecules and atoms and nuclei right down to the fundamental particles, the very building blocks of reality. All that is studied in physics. So in sum, what we're trying to do is understand the whole world around us, the whole universe around us at every level. Okay, so it's really ambitious in its scope. Okay, understand it on a fundamental level. But physics is not just about that. It's not just about understanding the universe and the world around us on a fundamental level. It's also about using that knowledge. Now, it's also about applying what we've learned about the universe, or learned about the physical world, to do useful things in the form of technology. So physics is also about using that knowledge, using that understanding of the world, for doing things, and this is by no means exhaustive, just a few examples. We have nuclear reactors, body scanners, lasers, microchips, things like the diagram you can see on the top right there, that's a schematic of a diagram based on the use of graphene. Graphene, as you may know, is this one atom thick layer of carbon, which is the strongest, most conductive material ever discovered here in Manchester. Okay? And because it's so strong and so conductive, that it's got lots of potential for use of nanoelectronics to make new technologies. So just some examples of how we use the fundamental understanding that is the basis of physics, a fundamental understanding of the whole world at all levels, to do useful things. But it's not, physics is more than that again. Physics is not just about understanding the world and using that understanding. But also, it's an approach, it's a method. It's a way of looking at the world, as a way of solving problems. To illustrate what I mean about that, here's another example. This is the Scholes-Black equation, as it's known. It's a big thing, okay? It won the Nobel Prize. It won the Nobel Prize, though, not for physics or even chemistry. It won it for economics. Okay? It's actually a physics equation. It's used originally, derived, to describe the process of diffusion. This is the process by which if I open, I don't know, a canister of gas over there, then it spreads throughout the whole room. Okay, that's diffusion. Now, Scholes and Black repurposed that equation and used it to describe diffusion of money through the economy. Okay? And it's such a revolution that it got the Nobel Prize. But it's a physics approach. It's a physics way of attacking a problem, a physics way of looking at the world. So when you come to university, you're not just learning about physics. Physics is something you learn to do. Okay? Physics is a set of skills as well as a body of knowledge. Okay? And that skills can be used in areas you might not expect. Not in physics, but other areas too. So that's what physics is also about at university. Okay, so that's what physics is about. That's the first of our questions. Now, in terms of the skills then, so these are just as important as the knowledge that you learn. What are the skills that you learn when you learn how to do physics? Okay, well, in learning how to do physics, you learn how to do certain other things within that. So physics is science, okay, and that means it's based on experiment. Okay, that's the fundamental building block. Science is based on experiment. And to do experiments, you have to know how to design and build and carry out something that almost by definition hasn't been done before. Okay, you're looking to make new discoveries, so you have to build a new experiment never been done before. Okay, and chances are that thing won't work the first time. Okay, and so you have to learn how to solve problems. Now, when it does work, what you'll get is data. Normally numerical data. On the face of it, that's just numbers, right? To draw meaning from that numbers, from that data, you have to learn how to analyze it and interpret it. Okay, that's a key skill. Okay, the analysis and interpretation of numerical data is one of those skills that you learn in physics, but can be applied in a whole host of different areas. Then you have to be critical and scrutinize your data. Does it tell you what you think it's telling you? Okay, does it actually consistent with what you thought you knew? Okay, have you done your experiment properly? Or have you, if so, have you learned something new? You have to be really rigorous and robust in your analysis. And then suppose that you make a new discovery. Yeah, if you then just keep that quiet, tell no one, then you've achieved nothing. Okay? Physics is also about communicating what you've learned, communicating what you've discovered through lectures and talks, and also through the written word in journals and books. Okay, so communication is also a key skill that you learn when you learn how to do physics. And the other key skill that you learn, or key process in physics, is that these days, when you learn, when you want to do an experiment, it's not usually done in isolation on your own. Okay, you do it in a team of people. Often you're using equipment that's very expensive. So basically, you have to persuade someone else, maybe the government's research council, or if you're working in industry, maybe you're a technical director, that it's worth spending money on doing this experiment, or learning about this bit of physics. Okay, so you have to learn how to persuade someone that it's worth doing. Okay, so persuasion becomes a key skill. So, just to sum up then, the skills that you acquire when you learn how to do physics, you need to have a critical mind. You need to be questioning and question whether we really do understand as much about the world as we think we do, or is it actually different, okay, and how can we tell? You have to be absolutely rigorous and robust in your reasoning. And experiments are a great way to do that. See, Mother Nature, she doesn't care. She doesn't care how clever you think you are. She doesn't care how beautiful you think your equations are. She doesn't care what you want to be true. She just cares what is. All right? And if you learn how to reason against experiments, you learn very robust and rigorous thinking. Okay, that's always testable. So you learn those thinking skills. And you learn how, as I said before, to analyze and interpret data, okay, which is data from an experiment, but it could be data from the stock market, or it could be data from a business spreadsheet. Okay? All these key skills you learn when you learn how to do physics. You learn how to work and manage groups because normally you do this stuff as a team of people, and you learn all the maths and the computing needed to handle all those data and all that numbers. And then finally you communicate, so you learn how to speak and you learn how to write to communicate what you've learned. All learned when you learn how to do physics. Okay, so that's another aspect of physics. What about physics in Manchester? So if you get the chance today, I hope you get the chance to go and visit the Schuster Lab, which is the building shown there. That's very much the home of physics in Manchester. So we have our lecture theatres, our teaching labs, many of our tutorial rooms. Okay, that's very much the centre of physics, even though we've spread a little bit beyond that, as I'll explain. Okay, but before I do that, let's talk a little bit about the history of physics in Manchester. We've had a physics department for over 150 years. Okay, and during that time, we've had no fewer than 13 Nobel Prize winners, okay, associated as either students or staff with the physics department. So they include people like Rutherford, this guy, who was the first person to split the atom here in Manchester just over 100 years ago, all the way to our most current two Nobel Prize winners. This is Andrei Geim and Kostya Novoselov, who won the 2010 Nobel Prize for the discovery of graphene here in Manchester. Okay, so that's some of the history and the pedigree, if you like, of physics at Manchester. What about the research? Now, Manchester is very much a very active research university, and that's important from a student's point of view, because one of the benefits of coming to study at a research university is you get to learn about the latest discoveries from the people making those discoveries. Okay, that's the benefit of coming to study at a research university. So what's the research like at Manchester now? I've talked to you about the history. Well, probably the best way to characterise it is by this exercise, REF 2021. This is, REF stands for Research Excellence Framework. It's a process carried out by the government every 7 years or so, where it assesses the quality of the research in every department in every university across the country. So this is the government exercise to rate research across all subjects, and these are the results for physics, okay, released in May of this year. So it classifies the research under 4 categories: 4-star, 3-star, 2-star, 1-star, with 4 stars world leading, down to 1-star reckoned nationally. Okay, and as you can see, each department got rated as a percentage under each of those categories. Okay, so you can see that Manchester got joint first for 4-star, the highest ranking, but more in the 3-star. Okay, so the very highest rating for research, not by us, but the UK government. Okay, and this, as I said before, is important from a student's point of view because you get to learn about the latest results from the people making the discoveries. Okay, so what's the physics department like in terms of not just bricks and mortar, but people? So we're a big department, not the biggest, but maybe sort of towards the higher end of staff, students. So we have about 90 academics. Those are the lecturers and professors who do the teaching. Okay, and we have supporting them, we have about 200 or so research and admin staff. And we welcome every year about 330 new undergraduates onto our programs across all the types of program, and about 70 postgrads. So we're a big department, which means that we're a large, vibrant community of physicists with a wide skill base. So one of the benefits of coming to a big department with a large number of staff is that we have experts across the full spectrum of physics topics, everything from cosmology to particle physics to graphene to biophysics to nuclear physics. So whatever it is you end up being interested in, whichever bit of physics you find the most fascinating, we've got an expert on the staff who can run a lecture course on it. You can learn about it from someone who's an active researcher in that area. So this is the benefit of coming to a big department. So I showed you a picture just before of the Schuster Lab, again on top left, which is very much the home of physics. We've sort of grown a little bit, we've outgrown the original building. So the building underneath is the annex. That's the sort of been more recent addition to the Schuster. It's about 5 years old now. So if you go on the tour of the undergraduate labs, you'll be taken through the annex as well as the rest of the building. And in the annex is where you'll see the first year labs, for instance. So it's a sign of the investment Manchester's placing in the teaching of undergraduate physics that we're going to spend, I think it was £10 million on that new annex to the building. So there's just a lab and its annex, the main home of physics. We've expanded a little bit, and so some of our staff have offices in the adjacent building. That's the one below, the Alan Turing building, particularly the astronomers. And the other pictures you can see there are all interior shots of various teaching spaces within the physics department. So again, if you go on the tour, you'll see all this for yourselves. So we're a big, busy, well-equipped department with good facilities. Now, how about the different physics programs that we offer? So we have two broad categories of program, either the 3-year bachelor's, BSc, that's the traditional type of degree, undergraduate degree that's been around for years and years and years, and then we also have 4-year MPhys courses. Now that's a more recent thing, about 15 years old, where it's still an undergraduate degree, okay, but it's 4 years, and you've got the extra year of learning compared to the traditional BSc. Now, there are no rules of thumb, which is best for you, but no strict rules, but a rough rule of thumb is that if you think you're going to use both just mainly the skills that you learn, then maybe the BSc is best suited to you. But if you're going to use the skills and the knowledge, then maybe you'll benefit from the extra year involved in MPhys. Having said that, and regardless actually of what you put down on UCAS form, those two programs are identical for the first 2 years. So we will ask you in any case, at the end of year 2, which you want to be on, BSc or MPhys, and swap you between them, okay? So even though you need to put one or the other down in UCAS form, it doesn't actually matter until the end of year 2, okay? So that's the two broad categories of degree program. We also have various types of degree within them. Most of them offered as either BSc or MPhys, with the exception of the Study in Europe option. So we have our main program, physics, and we also have physics with astro, physics with theory, physics with Study in Europe, and maths and physics. Now, for those courses that are physics with something, that means that you spend roughly 2/3 of your time doing the physics, the same physics as everybody else, and 1/3 of your time doing the other bit. So astro, theory, or Study in Europe. Okay. Now the final option, maths and physics, is a joint program. That means it's a 50-50 split between the two subjects, and it's jointly taught by ourselves and our colleagues in the maths department. Okay. Again, my advice is you should choose whichever of those you think you'd be most interested in. Okay, we see very little difference, or no difference really, in terms of what people go on to afterwards. And if you choose the one you're interested in, you're more likely to study hard and then do better. Okay, there are no differences in the entry requirements. So really, my advice is just choose the one you think you're most interested in. Okay, entry requirements. So our standard offer is A star, A star, A, where the A stars have to be maths and physics. So if you're what's known as a widening participation or contextual offer candidate, that's can be reduced a bit. But for a standard, which is most people, standard applicant is 2 A stars and an A. Now, obviously that's a very high offer, so I wanted to explain why it's so high. Under the UCAS system, if a university makes you an offer of a certain set of grades, any university, and you achieve those grades or better, then actually not only does the university want to take you, they have to take you. It's a legal contract. Okay. But there are only so many spaces on the course. There's only so many spaces in the lecture theatre, so much space in the lab. So we have to control numbers somehow. And at Manchester, we are heavily subscribed. We have about 1,800 applications last year for just over 300 places. Okay, so the only way we can control numbers, so we don't overshoot our capacity, is by setting the offer level at that level, at the high level. Okay, so it's just, if you like, it's just a function of supply and demand. Okay, because we're oversubscribed, we have to set at that high level in order to make sure we don't overshoot the capacity of the course. Okay, that's the reason. Okay, so that's the standard entry for in terms of A levels. Of course, if you're studying some other exam system, whether it be, I don't know, IB or some overseas system, then we'll just make you an offer of equivalent grades in that system. Okay, so let's imagine that you want to come to Manchester, you get the grades, you get an offer, and you arrive. What sort of things can you expect to learn in detail? What are the structure of the programs? So all our programs have a core plus option structure, which means that there's a number of key topics, the core topics, that everybody has to study. Okay, this is actually set by the Institute of Physics as part of the accreditation process. So they include all the things you would expect to find in the physics program, the relativity, the quantum mechanics, the electromagnetism, particles, cosmology, all those key topics, but they don't take up the entire timetable. So there's room in the timetable to study option. So things, bits of physics that you are particularly interested in and you choose to study. Okay, so level 1, level 2, and level 3 basically corresponds to years 1, 2, and 3. You'll see, as well as the core topics, you're doing things like energy sources, solar system in level 1, galaxies, high-energy astrophysics in level 2, level 3, interstellar physics, laser physics, nuclear fusion, etc., etc. Okay? You'll notice that the number of options is getting bigger as you go into later years. And that's because the core topics are mostly covered in years 1 and 2. Once you've got the essential material under your belt, you're then able to study any bit of physics that interests you. Okay, you have more options as you go forward. So you have lots of options in year 3, and if you're on the MPhys programs or in year 4, then actually all the lecture courses that you take are options. You've covered all the key core topics in physics by then, and now you're studying whatever bit of physics that are most interested in. Okay? So you do 8 lecture courses in your 4th year, and you also do in your 4th year a research project. In years 1, 2, and 3, you do lab, but you do it in the teaching labs, and those experiments are getting progressively more complex and sophisticated. So you'll see the undergraduate teaching labs as you go on the tour, but in year 1, you do experiments that are 2 days long. You do it 1 day a week, so it's 2 weeks. In year 2, you're doing more sophisticated types of experiments. You're using cryogens and vacuums and radioactive material. And the experiments are longer, up to 3 or 4 days long. Okay, still 1 day a week. When you get to the 3rd year, you're doing experiments that are now 8 days long. Okay, two 8-day experiments in your 3rd year. So really quite extensive, but still in the teaching lab. Okay, but if you're in the 4th year on the MPhys program, you leave the teaching labs and you're going into the research labs. Okay, you get embedded in a research group and you do a project which is 2 days a week and lasts the entire year. That's 48 days on a research project, okay, in a research lab. So it really teaches you how to discover new physics. Okay, so it's a key element of our 4th year. So that could be an experimental project, or it could be, if you're that way inclined, a theoretical project instead. Okay, so that's what we teach and the structure of our programs. The next question is, how do we teach? Okay, well, it changes somewhat as you progress from years 1 to 4. But to give an example, this is the structure or the schedule for the first semester of 1st year, as an example. So in that case, you're doing 5 different lecture courses, okay? 4 of which are core in that term, and 1 is an option. And each of those has 2 hours of in-person, in a lecture theatre lectures, clear, okay? And then you have lab, okay? You'll see those labs as you go around the building, that's 5 hours. And you have 2 separate hours of tutorials, okay? Whether in-person, live. So if a tutorials, if you're not familiar with them, are a form of small group teaching. So you have 1 member of staff and 4 or 5 students. These are really kind of labour intensive, if you like, because it's 1 to 4, 1 to 5 teaching ratio, but we think they're really important because this is your opportunity. You have to meet with your tutor once a week to discuss some of the ideas you'll have met in your lectures that are really quite challenging. You know, even in the first term of first year, you're dealing with relativity and quantum mechanics, and these are really difficult concepts, and you really benefit from being able to discuss them and talk them through with a tutor. So we're really keen on having tutorials, especially in the first couple of years. Okay, that adds up to 17 hours of what we call contact time, so that's directly being taught, you know. And that's, but of course, on top of that, you've got homework, essentially. So you've got question sheets associated with each of your lecture courses, and you've got lab reports to write up, for instance. So it's a full week's worth of learning, with the exception is that Wednesday afternoons are always kept free. That's true of all courses at university, because that's your opportunity to get involved in, you know, clubs and societies and student union activities. Because even though, you know, you've come to university to learn about physics, you've come to get your degree, that's not the only opportunity that university offers. You know, there's plenty of things you can get involved, whether it's, I don't know, music or sport or politics or whatever it is you're interested in. A big university like Manchester has a society that you can join to get involved in. So that's why we have always that Wednesday afternoon reserved. There's no teaching to allow you to do that. Okay, so that's how we teach. But of course, we're also very keen for everybody, every student, to do as well as they possibly can during their studies. So we have a number of measures in place to support you, make sure you do as well as you possibly can. So probably first and foremost, I would say, is the tutor system itself. So this is a regular weekly meeting that you'll have with your tutor. The first point of contact will be usually your tutor. Okay, there's someone you can come to. If something's getting in your way, stopping you studying, then they're the first person you talk to. They might not be able to solve it themselves, but they'll be able to signpost you where to get further help. Okay, so the tutor system, a regular weekly meeting, is very key. We also have an academic advisor. So your tutor, your academic tutor, will change from year to year, but you will also be given a member of staff known as an academic advisor who will be the same person for your entire 3 or 4 years. Okay, so that person gets to know you very well. You meet several times a year to discuss progress, exam results, option choices, things like that. Okay, they have an overview of your entire undergraduate career. Okay, so that's an important element as well. We also have a peer-assisted study scheme, PASS, where basically when you join as a first year, you're basically buddied up with a later year student who can give you sort of more informal sort of help and advice. So, you know, you want to know what is the best option to choose, you know, or what the best lab experiment is to choose, things like that. He's just someone you can talk to, another student who's been through the system a bit ahead of you, you need just someone to talk to. So that's also a useful thing. And of course, we're a big university, we're very used to dealing with students who might come to us with disabilities, so they could be physical or learning disabilities. So for instance, you know, if you're unable to write quickly in lectures, we make sure you get a printed version of the notes or someone to take notes for you. Or if you've got dyslexia, we might allow you extra time in exams. So we've got systems in place to make sure everybody does as well as they can. So let's imagine that you decide that actually physics is what you want to do at university and Manchester is the place you want to do it. You apply, you get the grades, you come to us and you have a great time over 3 or 4 years studying whatever it is you really love, like cosmology or particle physics or nuclear physics or graphene. And then after 3 or 4 years, you graduate. Okay, what then? What sort of careers can you expect to have access to with a physics degree from Manchester in particular? So I'm going to start off with a couple of case studies and then I'll give you some data to back that up. So here's just a couple of examples of recently graduated students. So for instance, we have Ellen here. She did an MPhys 4-year program And then her first job post-graduation was with Apple, okay, as a data analyst. So here's an example of someone, as I described before, who's not necessarily using the physics knowledge directly that she's learned, but rather the skills, okay, particularly the analysis, the numerical analysis and the computing skills she's picked up as part of her physics degree. Another example, another recent student, who was a project student of mine happens. This is Cayman. So he graduated also on the MPhys 4 years, but then he went to work for an academic journal. Okay, so academic journal is where you publish research papers, and he's an editor for that. So he manages the process by which people submit the journals, it gets assessed by the peers, and then eventually appears in publication. So there you need a physics knowledge as well as some of the skills you learned as doing the physics degree. So, some numbers. These numbers are taken directly from Discover Uni. Again, this is a government scheme, gather data about all the various programs across every university in the country. So you can look at the website and have a dig around yourself. They have different entries for each of our programs. So I've chosen as an example our most popular program, which is the MPhys in Physics. And you can see the sort of thing that people tend to do when they graduate. So roughly 2/3 go directly into employment, and about a quarter go into further study, largely PhD. In terms of the students who go into employment, it's about 60% who will then go into what you might call tech. So that's people who are using the physics knowledge directly. And then about 20% go into finance and business. So that's more the analytical skills, the numeracy. Teaching's only down at 5%, and then you've got a whole bunch of other stuff as well. Okay. So that's the sort of thing that our students do in particular. The other thing I wanted to show you is this, which was published about 4 years ago now. This was a study by the Institute of Fiscal Studies, which is a respected think tank, but it was commissioned by the Department for Education. And it was a study of the relationship between degree subject across the country and early career earnings. So there's two graphs here, one for men and one for women, taken from this report, but they tell basically the same story. So here we have a plot which has degree subject along the bottom and average earning at age 29 on the vertical axis. I don't know why they chose 29, but that's what they did. As you can see, they're in order, and notice what's on the right-hand side. This is the highest earning end. So there are some subjects in there you might not be surprised to see, things like medicine and law, but look at the others. What's the common link? Economics, maths, physics. Common link, numbers. Okay, analysis. Okay, those skills I mentioned before that you hone in the lab, okay, experimental data, are highly in demand in other areas. Okay, the reason that they're high earners is that those skills are key for businesses, for banks, for finance. Okay, and that's why physics graduates can expect earn these high salaries. So that's the data for men. The data for women looks very similar. In fact, physics is even higher up that scale on the right-hand side. Okay, but the story is the same. Okay, so it's those skills, the numeracy, the analysis that are highly saleable in the graduate job market, essentially. Okay. So we've got a very active, busy career service whose purpose is to help you transition from being a student to the world of work. So they've got all sorts of services that they offer to enable you to do that. Everything from practice interviews, psychometric testing, information days, milk round, all graduate fairs, all this sort of stuff that enables you to move from being eventually, I know it seems like 100 years away from now when you're sitting here being 17, but eventually you'll get a job, right? And this career services enable you to make that transition. And obviously you can access them throughout your undergraduate career, but also we don't just cut you off at graduation. You can access this for 2 years beyond graduation, okay, to make sure you get into that job that you want. Because, you know, some people take a year off or travel around the world or something. Okay, so they want to access it for about 2 years afterwards. Okay, so to sum up, physics at university is about understanding the world around us, the entire universe around us at every possible scale on a fundamental basis. It's also about using that understanding to do useful things, okay, make new technologies. And more than that, it's not only about doing useful things and understanding the world, but it's an approach, a mindset, a method of tackling problems and seeing the world, which is highly useful and highly saleable. Okay? So physics is about learning about all that, but it's also about doing stuff. Okay? Physics is something you learn how to do. Okay? And in learning how to do it, you develop a lot of key skills, okay, which you can then take out and use in your future career. Okay? And highly in-demand skills. Okay, so I've almost finished talking at you. Okay, I'll be answering questions in a moment. I encourage you to go on the lab tour that's around the physics department. From previous experience, what usually happens is after this talk finishes, most people in this lecture theatre try and go on a tour, right? And there's a huge queue and there's lots of waiting as a result. So if you're not rushing off anywhere, I encourage you to maybe go a bit later. Otherwise, you'll end up just standing in a queue. Okay, so let's try and pace it out so we can then have small groups going around. So I encourage you to go on the tour, but maybe not just immediately after this lecture. And then we've got a stand in the Schuster building as well. So any questions that you have that occur to you, you didn't ask now, but occur to you in 20 minutes time or an hour later, come and talk to us. And then hopefully we'll do our best to answer any questions that you might have. Okay, and if, for instance, you only think of the question on the way home tonight or next week or next month, then please get in contact. We'll do our best to answer them. You can look at the website. Many of the answers might already be up there or on our blog, but if they're not, then just send us an email and we'll get back to you as soon as we can. Okay, so that's all I wanted to say. So I'm happy now to answer any questions that you want. Please just stick your hand up, or if you prefer to come and talk to me one-on-one at the end, I'll also hang around for a bit as well. Okay, so does anybody have any questions about anything I've said here or not said? And I'll do my best. Yes?
It says on the UCAS application form that there might be an interview in Manchester.
Yeah.
Do you know when this is?
So what we do is, if we decide to interview, you apply, and then we will invite you at some date. We just do it in order between when you apply and the sort of, they can go up until March sometimes, okay? So I have to say, we haven't made a final decision on interviews this cycle because of recognising the fact that due to the cost of living crisis, it's quite a lot for some people to pay for lots of train tickets. So we'll be selective, I think. Hello? Yeah.
Do you need any prior computing skills?
No, we don't. The only thing we require from you is A-level physics and A-level maths. Okay, that's our starting point. We don't assume you know anything beyond that. Okay, any computer skills we'll teach you. Yeah.
So for further maths then, so you would expect them to have done further maths?
No, so it's A-level physics and A-level maths. Right. So further maths, great, but we don't require it. Your third A-level could be geography or German or music. Could be. It doesn't matter.
Would be at a disadvantage.
No. No, we have no requirements for the subject for the third A-level. Sorry, yes. Was there one over here? That one, sorry.
With the standard offer, it also mentioned contextual offers.
Yeah. So this is a nationwide scheme sort of instigated by the government to widen participation, it's called. That's trying to encourage people to come to university from backgrounds, postcodes, schools who hadn't normally, or don't normally send people. So what happens is you apply, you don't have to do anything, you just apply and then you get assessed. And essentially, if you're from one of these schools or postcodes that haven't sent along people into universities in the past, then you would get a relaxed offer as a result, yeah, by up to 1 grade or 2 grades. Yeah. Yes?
Is there any advantage of putting your UCAS application earlier than the closing date?
No. So the normal application period is starts whenever it is, late September, runs till January, whatever it is. All applications received in that period are treated equally. Yeah, that's the normal UCAS rules. That's the same for every department, every university. Yeah, aye. So what we're trying to do when we assess people UCAS forms is we want to make sure that we're accepting people in a course who are able to do well in it and flourish. We don't want to accept people who will struggle. Okay, that's the ultimate objective, right? And whereas if you've done, I don't know, stuff like, I don't know, you're captain of the cricket team, or you play the oboe, or you've traveled around the world, that's great in terms of your own personal development. It doesn't say anything about your ability to do physics. Yeah, so it's not really a surprise to anybody. The single best predictor of doing well in our course are A-level grades. So that's the main thing. So your personal statement is of really minor importance. So I would say don't sweat over it, right? It's A-level grades are the thing that actually predict whether you'll do well in our course. And so that's the thing we focus on. Any more? Yes? Okay, so that's our only program that's only available as a 4-year MPhys, because the 3rd year of 4 is spent studying abroad at one of our partner universities. So the idea is that you learn, in the first 2 years, you learn whatever language it is to a high level, so sufficiently high that you can go abroad in year 3 and study physics, but in a foreign language. Okay, so that's really high level physics, higher level language skills. So to do that, it would be probably too much of an ask to have someone who knows nothing of a language to get to complete fluency in 2 years. So we generally encourage people with already prior knowledge of a language to some degree. But regardless, when you arrive, we will give you, or rather the language school will give you an assessment of your language level when you arrive, and then design a program of language learning for the first 2 years to get you up to that level of fluency for year 3 to enable you to go abroad and study physics. Now, most of that language learning is done by the language schools, but because you'll be learning physics when you're abroad, you'll need to know physics technical terms in French or German or Spanish or Italian. So that means in your 2nd year, while you're still in Manchester, we'll give you tutorials, physics tutorials, but in that language by a native speaking member of staff. Yeah. So in terms of where you go, we have partner universities. By the way, this is completely unaffected by Brexit or anything like that. It's just individual relationships between universities. We have partner universities. So there are places like one of Paris universities, Paris 6 it's called. We have one in Munich Technical University, Berlin, Madrid, Trieste in Italy. So we have these definite partnerships, and that's where you'll spend your 3rd year if you go down that route. Yep. If you're all right at the back, sorry. Yes. So for both maths and physics and the physics with theory, people in those programs do half the amount of lab as someone on the regular physics program. You still do some lab, okay, but half the amount. And the extra time, you know, when you're not in lab, you're doing additional lecture courses instead. Yeah. So was there another one over that way? Oh, yeah.
How do you go about selecting applicants, given you have to reject 5, 6, and you're only doing it on the basis of grades?
So, because from prior experience, if we set our offer grades, because things don't, well, 2 years ago was the exception, as you're probably aware, but normally, and this has been the case since 2020, the overall grade profile doesn't change that much, which means from previous experience, we know that if we set our grades at A star, A star, A, we will get about the right number of students. So, because it's not a rapidly changing function, it's, you know, you can set it every year and adjust every few years if you need to, but it's not that, it doesn't change that quickly. Yes?
With the physics and astrophysics course, would there be any, so you mentioned that the maths and physics and maths and theoretical physics, you have less lab time.
Yeah.
Is that the same for physics and astrophysics, or is it replaced with like telescope work?
So you do the same amount of lab, but you're right. So the astrophysics, you're spending a third of your time doing the astrophysics part, which includes lecture courses and astro lab. So, I don't know if you know, but the Jodrell Bank radio telescope, which is part of our department, it's about 20 miles south of here, but it's part of our department. So, for instance, we have experiments that students go out to use the facilities at Jodrell Bank, especially in the third year. But we've also, as you'll see in the lab tour, we've got dishes in the courtyard, we've got optical telescopes on the roof, we've got telescopes you can use from within the labs. Okay, so you do astro experiments as part of your lab. Yeah. Any more? If you're waving your hand, oh yeah, go on.
In what sort of capacity is the uni connected to the Dalton Institute?
So Dalton Institute is basically part of the university. It's just that aspect of it which is particularly involved in nuclear engineering. So they've got a site up in Sellafield, but it's part of our research infrastructure.
In one of the research labs of like 40 of you?
So we wouldn't send you all the way to Sellafield because that's too much paperwork to get you to near that amount of radioactive stuff. Yeah, so we have a lot of nuclear physics. We've got a long history in Manchester. The atom was first split by Rutherford here. We've got an active nuclear physics group, and nuclear physics experiments are taught in the lab. In terms of people wanting to go on to have a career in the nuclear industry, the usual route is we're part of this consortium, which is called NTEC, Nuclear Technology Consortium, which is basically a postgraduate master's level, which is basically how people get trained for the nuclear industry. Yep.
How do you use predicted grades in the application process?
So basically, predicted grades, teachers are usually, it's very rare that they underpredict. Almost always either accurate or overpredict. I guess the principle is that, you know, teachers will tend to predict the grades they think the student could get on a good day. Okay, to do anything else would be unfair, I think. But then, of course, not every student has a good day on the exam. So actually, that was really the reason for the grade inflation 2 years ago, because predicted grades are higher than actual grades. So anyway, where we use it is if you're predicted to get the grades that we're asking for, then we'll basically make you an offer. Yeah. And if you're not, then we won't. It's essentially, and that is basically, as I said, the way we control numbers, because we know that level of grades will give us about the right, you know, in terms of the people who typically apply to us, who receive an offer and then put us first on the UCAS form at the end, and then actually get the grades. After all those factors, we get about the right number. 1,800 comes down to 330. And it's just because it's broadly the same every year, and so we can control it that way. Yeah. Yeah. Oh, sorry. The guy behind and then the girl in front will do it that way.
Do AS levels have any effect on that?
No. It's 3 A levels, that's what we look at. Yeah, maths, physics, and the third. Yeah, so you're in front?
You know how you
No, sorry, the girl just in front of there, yeah. Oh, sorry, sorry, my mistake. Sorry, Ben.
you know how you mentioned if you got a grade higher than the standard grade, the university is obliged to take you. Is that true for all universities?
Yeah, so the offer is, you have to meet that offer or better. You know, it would be perverse to say, oh, you got too good a grades, we'll turn you. No, that doesn't work. That's not how it works. You have to meet the offer grades or better, right?
What proportion of your postgrads are Manchester physics undergrads?
I think it's about a quarter, from memory. I don't have the hard numbers on top of my head, but it's about a quarter. Yeah. Any other? If you're waving your hand, wave more vigorously, because I can't see you. I can't see any hands waved vigorously or otherwise. Okay, so I'm going to hang round for a bit at the front. So if you prefer to talk to me one-on-one, I'm happy to do that. I encourage you to go on the tour, but just not all of you now, please, not all of you now, because otherwise we'll have a massive queue, okay? We're on the stand now, we'll be on the stand for the rest of the day. So any questions that occur to you half an hour from now, please come and seek us out. Okay? Right, hope that was useful.